So today we will talk about error correction codes, methods to find errors in our messages. So to do this, I will share the screen. And so today's topic is error correction. So last time we talked about error detection. So when we send ones and zeros, we can put parity bits, and that way we can detect 1 or 3 or 5 or 7-bit errors. We can use the parity on steroids method, where we calculate parity on positions of bits in words, in bytes. Then we also studied about checksum. We send some data and we add all bytes together and add that to the end of the message. And so the receiver does the same process and compares if his result was the same as the transmitted result. And if it's the same, then he knows that the message was received correctly without bit errors. And if they differ, then there was a mistake somewhere. And the same goes for cyclic redundancy check, and also for the very complicated encryption algorithms, which also calculate some check byte or check word or check string to detect errors. So today we will talk about similar algorithms, but they are, you would say, even better. We will talk about algorithms that not only detect errors, but are also able to correct errors. And how can we do that? How is it possible to send data, have it corrupt on the way, and then to be able to restore back the original data? Actually, the principle is relatively simple. So let's look at the example. Let's say you want to send message 10101100. So the idea is that instead of sending just one bit, you will expand it to several bits. So instead of sending one, you will, for example, send 1111. And instead of sending 0, you will send 4 zeros, 0000, and so on for every bit. So this one turns into 1111, and this 0 turns into 0000, and so on. And what happens is, receiver, let's say, for example, that some bits are changed. For example, this bit over transmission was damaged and turned into 0. And this bit, for example, changed to 1. So what the receiver does is the receiver receives 1 0 1 1 0 0 1 0. So the receiver looks at the input and it compares it to the original codes. So the only possible bit strings that it should have received are 1 1 1 1 or 0 0 0 0. It should not have received anything else. So what the receiver does is it compares each 4 bits to these two options and selects the one that is most similar. Okay, so it received 1011. 1011 is more similar to 1111 than 0000. So the difference between the received byte and 1111 is just one bit is different. However, comparing to the other one, to the 0000, 3 bits are different. So we would call it a distance between input and output. So distance between input and the correct possibilities in first case is just 1, and the distance between 1011 and 0000 is 3. So since the input is more similar to this, the receiver chooses the one that is more similar and corrects it to 1111. And in the second byte, so it received 0010 instead of 0000. So it again goes to the two possibilities that it should have received, and it checks out, okay, so here are 3 zeros and just 1 1. So the difference between this and that is 3. And when comparing to the other possibility to 0000, only 1 bit is different, so the distance is 1. So it says, you know what, this input is more similar to 0000, so I will choose this and correct the input to all zeros. As a result, the algorithm was able to correctly replace the input which was damaged with the output that is, the same as the received bytes. Okay, it's actually quite simple. So this is, the very, very basic, simple principle of error correction methods. Now we need to, maybe make them a little bit more advanced and also evaluate if, how strong this algorithm is. So let's say, for example, 2 bits are changed. During the transmission, 2 bits are damaged, some electromagnetic interference, and 2 bits change to 0 0. Here the problem is that since the receiver received 1 0 0 1, in this case, it compares it to two available possibilities, and this distance, or difference between 1111 and 1001 is 2. Difference between 0000 and 1001 is 2. So in this case, it's impossible to tell whether this was one damaged bit or 2 damaged bits. So it's impossible to tell if we had 0000 with 2 ones replaced, or 1111 with 2 zeros replaced. So as you can see, expanding 1 bit to 4 bits allows you to detect 2-bit errors and correct 1-bit errors. So error correction methods usually do both detect errors and correct errors. So I'll write it down here. For example, this simple 1 to 4 expansion, it allows 1-bit correction and 2-bit detection. And if 3 bits are changed, then it fails. It replaces the data with the wrong data. So if, for example, we send 1111 and 3 bits get flipped, then of course this algorithm will make a mistake. It will replace the received byte with the wrong byte. But well, that's, we can't fix all the problems in the world. So I see there is a question. So in 1001, how will it correct? Unfortunately, it will not be able to correct. It will have to just discard the entire message and send back to the sender that it didn't receive the data correctly. So in that case, unfortunately, this algorithm says, sorry, impossible to correct. So yes, it will just detect error. So, um, as a result, we can make this, you know, conclusion that, for example, this 1 to 4 expansion, it is okay, it is very good in cases where we can expect 1-bit errors or maximum 2-bit errors. But if the transmission line or air is very noisy, then this algorithm is just not good. For example, you can use it in cable communication. Cable communication rarely, if ever, has some um, bits flipped, and so you could use it there. However, uh, this algorithm adds a lot of overhead. You see, instead of each bit, we send 4 bits. As a result, our data speed drops 4 times. So, probably this algorithm wouldn't really be used in real life, but it is, the basis of understanding how this works. So if we wanted to be able to correct more bits, we would need to expand each bit more. For example, each one would be expanded to 5 ones. So, for the sake of example, let's see, if we expanded 1 to 5 ones, so if we swap 1 bit, we can detect it and correct it. If we swap 2 bits, we can uh, correct it. But if we swap 3 bits, unfortunately, it will think that it's more similar to zeros than to ones, and it will correct it to the opposite bit, so it will make a mistake. So we can just add more bits in expansion, and we expand the number of bits that it is able to correct and detect, but also we're slowing down the data transmission channel. So we would use this method in cases where we want to, do less retransmissions and where the channel is not really that noisy. We can only tolerate 1 bit on every 4 bits. So, the noise is 25% of the data. So actually it's a pretty good algorithm. It's an okay algorithm. It has its limitations. So it is good when we have random errors, but it's not good if we have burst errors. Okay, so this is the naive 1 to 4 expansion algorithm. But a little bit better algorithm is so-called Hamming codes. So the idea is that it calculates parities and puts them in special locations inside the word. So, where's the example? So here's the parity bits and the data bits. So for example, let's say we want to send 8 bits of data. And there was a very good example. Let's just search for it. So here's the example, the algorithm. Okay, so here it is. So here are 4 redundant bits and 7 data bits. Data bits are in position 3, 5, 6, 7, 9, 10, and 11. So 1, 2, 3, 4, 5, 6, 7. Okay, let's do the example. So for example, let's just calculate the example that we have here. So we want to send these 7 bits, 1, 0, 1, 1, 0, 0, 1. I'll write it here. Let's say we want to send 1, 0, 1, 1, 0, 0, 1. So yeah, it is 7 bits, but ASCII table was originally for 7-bit letters. So sending 7 bits, it's not that uncommon. And first we position the data bits in the resulting 11-bit word in the correct positions. So we have 11 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the bits go in the following places. The locations which have which could be calculated as 2 to the power of n are for parity. So I'll draw them in red. This is parity. So this is bit 0. This is bit 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Actually, if we wanted, we could also have the bit 11 as well. Doesn't matter. So the locations which are powers of 2 are for redundant bits. So location number 0, number 1, I guess in this example they are counting from 1, but I don't think it is correct. So this would be location 0, 1, I think 2, 4, and 8 would be correct. And let's do it on 8-bit data. I don't know why it's 7-bit data. Whatever. So or maybe I'll just open the book. Also, I think I put in Artus a link to a book, which is really good about computer networks, and it also describes these algorithms. It is called Computer Networks. Let's write PDF. Oh, it's right here. And its author is Tannenbaum. Error correction codes, Hamming codes, right there. Sample here. Okay, here's a better example. So in this case, basically, the bits that we want to send go into the locations that are not powers of 2. So for example, location 1 is 2 to the power of 0. So this will be for parity. Position number 2 is 2 to the power of 1. It's 2. So this is also for parity. So the first data bit, this 1, goes in only location number 3. Next is position number 4 is 2 to the power of 2 is 4. So this is also for parity. So these 3 zeros are these 3 zeros. Position number 8 is also for parity because 2 to the power of 3 is 8. And the last are the 3 data bits as well. So what happens here is parity bits are calculated based on the value of the position bit in the following way. So let's work out the example from the book. It's better. This algorithm is not really that simple. So, maybe I'm stuttering a little bit. So, so this is for parity. Yes, they were counted from 1. So this is 1, 2, 3, 4. This will be for parity. 5, 6, 7, 8, 9, 10, 11. And parity bit will also be this. And so let's write the bits inside. So here is 1, 0, 0, 0, 0, 0, 1. So this is first and this is last. And the idea is that the parity bits are calculated for those locations which contain the certain parity bit when expanded as sum of 2's exponent. So for example, 3. 3 is 2 plus 1. So 3 will be used to calculate parity bit number 2 and parity bit number 1. 5 is, for example, 4 plus 1. 4 plus 1. As a result, 5 will be used to calculate parity bit number 4 and parity bit number 1. 6 is 4 plus 2. So 6 will be a part of parity bits number 4 and number 2. 7 is 4 plus 2 plus 1. So when we calculate parity number 4, 2, and 1, we also use the 7 bit. So we use, to expand this calculation, we only use the powers of 2. 2 to the power of 0 is 1. 2 to the power of 1 is 2, 4, and so on. So some bits will be only parity and some bits are only data bits. So 8 is power of 2, so this will be used for parity. 9 is 8 plus 1. 10 is 8 plus 2. And 11 is 8 plus 2 plus 1. Okay. If we do this, then Let me check. Then we need to calculate the parity, and let's see if it was odd parity or even parity. So in my opinion, you could also put the bit number 12 because 12 is 8 plus 4. So I don't know why they only have examples with 7 bits, but fine. So let's see how the parity is calculated. Is it even or odd parity? That is the question. Each check bit forces the modulo to sum or parity of some collection of bits, including itself, to be even or odd, so even parity. So let's say, for example, so the calculation of parity now is the following. So if we will, for example, want to calculate the first parity bit, the parity bit number 1, we need to look for numbers which contain 1 in their 2's expansion and only use those bits. So as you can see, data bit at position 3 is 2 plus 1. 1 is here, so we will use it. Bit number 5 also contains 1, so this will also participate. Number 7 also has 1, so this will also participate to calculate this 1 bit. And this 9 also, and bit number 11 also contain 1. So let's calculate it. Position number, yeah, let's write them down. So bit number 3 is 1. Bit number 5 is 0. Bit number 7 is 0. Bit number 9 is 0. And bit number 11 is 1. And now we need to calculate parity only on these 5 bits. So the parity is even parity. It is so-called make it even. So, so to make it even, the number of ones need to be even. There are 2 ones, so it is already even. So we don't need to add 0 to make the number of ones even. So this bit is 0. Okay. Next, position number 2. So 2 is used for bit 3, for bit 6, for bit 7, for bit 10, and 11. So for 2, it is bit number 3 is 1, bit number 6 is 0, bit number 7 is 0, and bit number 10 is also 0, and bit number 11 is 1. So, well, in this case, the number of ones is even, so we don't need to add 1 to make it even, so we add 0 to keep it even. Next position is position number 4. So 4 is right here for 5, for 6, for 7, and that's all. So bits number 5, 6, and 7 are 0, 0, 0. There is an even number of ones, so this parity bit is also 0. And next 8, 8 is for bit 9, 10, and 11, which is 0, 0, and 1. And to make the number of ones even, we need to add 1. So now it will be even. So the parity bits turn out to be 1, 0, 0, 0 in this particular example. So we have done this complicated calculation. You know, if you know it, it's actually simple, and you can also write a program or a software that calculates it automatically, or you can also build an electronic circuit which calculates these bits automatically, because they are just XORs of certain positions, and we can easily make them in hardware as a hardware accelerator, and they are calculated basically automatically online. And now you will see some magic, which will explain why we did all of this complicated bit expansion and stuff like that. So this is our original data. Let's follow the example. So what we do now, we write the check bits in the opposite order. I wonder why this is. Okay, now I get it. So let's say we send the data, and of course, if we send the data without a mistake, then you know, there's no error. But let's say we send data 1, 0. Let's follow the example 1, 0, 0, 1, 0, 0. And then data bit number 5, let's say, is flipped. You know, there is a mistake. So it should have been 0, but during the transmission, it experienced the error and we received the opposite bit. And the other bits are the same. Okay. So let's do the parity calculation for this. So parity bits are bits number first, second, fourth, and number 8. And let's do the calculation and calculate the parities again. So, but on this message that has errors. So I'll use a different color here. So to calculate parity bit number 1, we use bits number, basically all odd bits. So we use this, maybe with the pink, for example. So we used for this bit 1, 5, 7, 9, and 11. So we count how many ones we have. So 1, 2, 3. So 1, 2, 3 bits. So for this position, we used bits 1, 0, 0, 1, 1. It's 3 ones. So this, on our side, when we calculated, it is 1. So we see that we have received data with errors, because right there, we have the first difference. Let's calculate parity for parity bit number 2. So for 2, we are using bits number 3 again. 2 also is inside 6, bit 6. In bit 7 also in bit 10 and 11. so in bit 10 and bit 11. So let's calculate the parity for the bit number 2. Okay, so 5, 1, 2, 3, 4. So 1, 0, 0, 0, 1. We have two ones in this case. So this bit's value is 0 because we already have even number of ones. So 0 is right here. It's the same. So we know, okay, for these bits, there's no mistake. Next is parity bit number 4. I'll take again different color, for example, this bright green lime. So number 4 is used in 5, in bit number 5, in bit number 7, and that's it. Is it? Oh, and bit number 6. So bit number 6 also. So let's calculate parity bit number 4. So 1, 0, 0 tells us that we should have additional 1 to make the number of ones in this subset even. So this parity bit is 1. And we see that we received 0. It should have been 1. So here again is the mistake. And let's calculate parity bit number 7. I don't know what color, for example, orange. So parity bit number 8, parity bit number 8 calculates on bits number 9, 10, and 11. Let's see. Parity bit number 8 is used in 9, 10, and 11. So we count the number of ones. 0, 0, 1 has 1, 1. So we need to add 1 to make the number of ones even. So we have this right here. So did I calculate everything correctly? Okay, so did I make a mistake here? So 1, 1, 0, 1. So error syndrome is this. I'm not sure if I didn't make some mistake in the calculation. 0, 0, so why did I get 1? I should have received 1, 0, 0, 0, 1. One second. I've been, calculating this for several years, but this year there's some mistake, I guess. So why is it calculated differently? 1, 0, 0. Let's see. Which bit did I change? 1, 0, 0. Okay, so I guess in this case, it should show me that the mistake is in location number 5. So 5 goes into 4 and 1. Okay, so the result should have been that this string is equal to 5, and it tells me that the mistake is in position number 5. So I guess I have to do XOR on the parity bits that I received and the parity bits that I calculated. So this parity bit is the same. So basically we know that the mistake is not in locations number 11, 10, and 9, because the parity bit number 8, which is calculated on these three numbers, is the same as the one that we received. So the sender calculated parity on number 8, it's the same as our parity. So we know that the mistake is not in these 3 bits. So we actually can automatically say, okay, the parity bits are different in some locations, but these these 3 locations should be fine. Okay. So, and this is the same. Next, if we look here, the parity bit number 2 is the same. So we also know that since parity bit number 2 is used for locations number 3 and 6 and 7, then bits 6 and 7 also are correct, okay? Because parity bit number 2 is the same. So we know that the mistake is not in those locations on which we calculated this parity bit. Next, we check out the parity bit number 1, in the first location, in the location number 4, and basically it tells us that the error in that location, which has a different parity. So, location number 1 plus location number 4, the parities are different, which basically leaves us with the conclusion that the only possible way for error is right here in location number 5. So we need to flip location number 5 because all other parity bits were the same. So all other bit locations are actually correct. So we do the parity XOR on input and output. And what happens is 0 XOR 1 is 1, 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0. We have 0, 1, 0, 1. If you use calculator for programmers and write 0, 1, 0, 1, it says 5. So we know that the mistake is in bit location number 5. Okay, so we change the bit in location number 5 from 1 to 0, and we get 1, 0, 0, 0, 0. Here we change to 0, here we leave 1, and as we can see, the output data 1, 0, 0, 0, 0, 0, 1 is the same as input data that was sent through a noisy channel 1, 0, 0, 0, 0, 0, 1. Okay, so yeah, now I remember. So this is how Hamming algorithm works. So the idea is that each parity bit is calculated on different locations and in such smart way that when we recalculate the parity on a damaged string, then XORing it with the parity locations, it tells us exactly where the mistake is. This is why the parity bits are in these weird places in position number 1, 2, 4, and 8. And this is why they are calculated in this a little bit complicated manner, because putting them there really helps us to calculate where the mistake is, okay? And so now we can do a little comparison. So if you have some questions, you can ask them in the chat box. But we can do a little comparison between our naive 1 to 7 conversion and the Hamming code, for example, which is 7 to 1. Okay, so let's do a little comparison. So, okay, we will try a different example in a second. So let's do a little comparison between these algorithms. So first is 1 to 4 simple expansion. So it makes um, 1 to 4 simple expansion increases data amount 4 times. So it is 400% increase in data length. Corrects 1-bit errors, detects 2-bit errors. Hamming codes so it increased the number of bits from 7 to 11, right? 7 plus 4 is 11. So by how many percent did it increase? So 7 divided by 4, oops, sorry, 4 divided by 7, by 57%, so it's 157% increase in data length. So, you know, there is a difference. So first algorithm created 4 times more data, and this adds only 57% to the original length. Like this, and corrects 1-bit errors, but it doesn't really detect more bit errors. If you have 2-bit errors, then this algorithm will probably fail, because it always calculates a number and says, you know, if we have 1-bit error, then that error is in that particular position. But if you know, if you have, for example, 2 bits in as errors, it will not detect them. However, you know, you only added 57% to your original data. So in channels where you can expect only, you know, infrequent 1-bit errors, this Hamming code is really much, much better than this 1 to 4 simple naive expansion. Okay, so I don't know, maybe I wrote something down on. So you wanted to try to do another example. Maybe we can do it in Excel. Maybe it will be a little bit, you know, better. So let's say we want to send data bits 1, 0, 1, 0, 1, 1, 1. So we have 7 bits, 1, 2, 3, 4, 5, 6, 7. Then we need to copy them, and so this is data bit number 7, data bit number 6, data bit number 5, data bit number 4, data bit number 3, data bit number 2, data bit number 1. Maybe we need to center them. Now we need to calculate parities. So we will have parity bit number 1, parity bit number 2, then we will have data bit number 1, then we will have parity bit number 3, or maybe, okay, so then we will have data bit, or maybe it's better to copy. Then we will have data bit number 2 and 3. Let's see in this example. So parity bits are, here are 3. Okay, so here are 3 bits. Then we have parity bit number 4. I think it actually should work on 8-bit numbers as well. So this is how we will send the data. And now I'll write also over them the bit positions, starting from 1 in this case. So this is 1, this will be 2, and 11. Okay. Now let's copy the data. So data number 1 will have values there. I guess I can just copy them like this. So these are the data bits. Data bits will be, for example, light blue. And now let's calculate parities. So parity bit number 1 will be in all locations which divide, which are odd numbers. So it is equal to, and how do we calculate XOR in Excel? I think we can do it. Oh, here it is, XOR of this position, also 5, and also 7, 9, and 11. So it says false, but it should actually say 0. So if XOR equals to true, then write 1, else write 0. So now we have number 0. Next is parity bit number 2 will be calculated on all locations which contain 2 when expanded as the sum of 2's complements. So parity bit number 2. I think that parity bits don't calculate on themselves. Parity bit number 2. So 3 is 2 plus 1. I'll actually copy this formula and paste it here. And here in XOR, I'll just manually write it down. So XOR on 3 is 2 plus 1, so this participates. 5 is 4 plus 1, so not here. 6 is 4 plus 2, so this participates. 7 is 4 plus 2 plus 1, so this also participates. 9 is 8 plus 1, so this is skipped. 10 is 8 plus 2, so 2 is there, so it is also used. And 11 is 8 plus 2 plus 1, so this is also used. And parity bit 2 is 1, so 1 plus 1 is 2 ones, 3 ones, so we need to add 1 to make it even number. So position bit number, parity bit number 3 is for numbers that contain 4. So 5, I'll just use the same formula. So 5 let's try again. This 5 contains 4. 6 is 4 plus 2, so this also participates. And 7 is 4 plus 2 plus 1. And 9 is 8 plus 1. 10 is 8 plus 2. And 11 is 8 plus 2 plus 1. So that's all for this guy. So parity bit is 0. And for 8, it's the same formula, but for 8, 9, 10, and 11 participate. So we have this thing here. So now I copy this message, and let's say that I I'm going to swap some bits. So let's say we have so that it shows up correctly. So parity bits will be calculated automatically. So let's see. Let's say that we are sending data 1 0 1 0 1 1 and 1. So if we send the same data, the parity bits are the same, so difference between parity bits doesn't exist. Their XOR calculates to 0. As a result, the error is not there. But let's say we change one bit. Let's say I'm going to change this bit from 1 to 0 manually. What happens is the parity bits are different. Parity bit number 0, and here's number 1, so here is the difference. Parity bit number 3, 0, 0, here is no difference. Here 1 and 0, there is difference. And here 0 and 1, there's also difference. And if you take a calculator in programmer's mode and you write 1011 in binary 1011, you see that the result is 11. So the differences between parity bits tell you that the mistake is in location number 11. Well, if you think about it, that's because parity bits number 8, 2, and 1 participated in calculation for parity bit number 11. So since all 3 of them are incorrect, it must mean that bit number 11 is wrong. Because, for example, bit number 4, parity bit number 4, it did not participate in 11 calculation, and it is correct. So the mistake must be only in location number 11. If it was in a different location, then the combination of parity bits would tell you it because it would be different. So this is how the Hamming error correction algorithm works. So it calculates the parity on data, and it basically tells you, so the difference between the parity bits tells you the location of the mistake inside of this transmitted data. Okay, so maybe now you understood it better. You can write in the chat box if you understood it or not really? Okay, so that's the Hamming code. And yeah, okay. So there are also other more complicated error correction codes. For example, this convolutional code used for GSM. Here is NASA coming up with their own convolution codes. So, you know, the algorithm is a little bit similar. We're not going into detail because it will be, you know, a bit complicated. But generally, there is also the convolution codes and so on. Yes, so this book is the best book in the world to study about computer networks. This Professor Tannenbaum from Netherlands actually has participated in development of the internet and of computer networks, wireless and wired, right? So this is a standard book that people would study for computer engineering. At the same time, it has a lot of information also about for electronics engineers. It covers everything from radio transmission and cable transmission and some problems to error detection and error correction codes. It also talks about routing, about application, about security and encryption. So actually our subject is closely related to this book and actually follows the same pattern. In labs, we are trying to implement the ideas of this book uh, in our development kits, sending data forward and back and doing some error correction and detection and so on. So this book, I highly recommend it to you. And it's actually very interesting and it's written in a very nice, easy to read manner. It talks about the history of computer networks, how the first networks were invented and what problems they had and the reasons why they even started to build these networks and how they expanded and so on. So this is a very, very good book by a person that has actually participated in the development of computer networks. So he really knows what he's talking about. Okay, so that is all about error correction and error detection codes. Let's see. Error controls right there. So the next topic is the network layer, where we are going to talk about routing algorithms. But I think it's best to not start this topic today and maybe leave it to the next lecture because we don't really have that much time left. And I'll start to talk about it. It's not gonna, work, and I will not finish. So maybe that's all for today. So today we studied about error correction codes. We looked at two algorithms, and the rest is probably for the next time. Okay, so so I cannot upload the book on Artus because I think it is copyright protected. You can find it on the internet, but I'm afraid that if I put it on Artus, we can have some copyright issues and problems, because we would be supposed to buy the book, um, you know. So I better not upload it in Ortus, but you can find it in the following way. You open the browser and you write in computer networks, Tannenbaum, and for example, PDF at the end. And you can find it here, 5th edition, 4th edition, and so on. Every few years, this guy updates the book. Ta. I have uploaded the test. I'll check it out. Ta Ortus. So I suggest that you do the test right now, for example, if you want to, or as early as possible, because this test, I think it was about the hardware layer, the physical layer. And, while you still remember something about it, I suggest that, you just sit down and do the test. I think that the test was actually really simple, so let's see what the test is. What frequency bands can you use in Europe without license? You can check it out on this document called ISM Bands TI from Texas Instruments. Texas Instruments is a producer of radio frequency chips, and they actually have made this really nice PDF document where, yeah, the first one is actually the correct one, compliance overview. And it's not really complicated document. It basically tells you what frequencies you can use. For example, blah, blah, blah. Frequency bands for non-specific short-range devices in Europe: 433, 868, and 2.4 gigahertz. So in this test, I just check 2.4, 433, 868. So that's the answer to the first question. Next is increasing center frequency allows for. So if you increase the frequency, for example, from 43, 433 megahertz to 2.4 gigahertz, increasing allows you to get higher speeds. For example, 5 gigahertz router is even faster than 2.4 gigahertz router, so higher bit rates, higher data speeds. If the frequency is low, then also the bit rate will be low. Increasing the transmit power. Choose one. It says choose one or multiple. It's in Latvian, I guess. So increasing the transmit power. If you increase the transmit power, if you transmit louder, it consumes more power. That's true. Yes, because you're spending more energy, but it increases range. The louder you shout, the further away people can hear you. At the same time, the louder you shout, the more energy you need, and it drains the battery. Okay. Next is, what is the maximum TX power in 868 megahertz band for non-specific devices? You go to this document. It says basically plus 14 dBm with no limits. So you just check plus 14 dBm. Aha! This is a trick question because 868 megahertz, 14 dBm. This is in dBm, but you need to convert it to milliwatts. So let's try to do this. Online, you can go online and search for dBm to milliwatts, and you can just click here and write in dBm 14, convert, it's 25 milliwatts. So in this, you just select 25 milliwatts. Increasing the RX bandwidth. So bandwidth, you make it wider, so more noise goes in. So more noise means that you have less range. If you just take RX bandwidth and make it wider, then you need, oh yeah, and by the way, the second answer should not be done randomly. RX bandwidth must be precisely calculated. This would actually be the correct answer, right? Because you can't increase or decrease it randomly. It should be equal to TX bandwidth plus a small safety margin because of the crystal precision. So this is the correct answer. Should not be done randomly. That's true. It needs to be calculated. And I gave you the formula. Next question, what is the deviation in FSK signal in frequency domain? So it's difference between one frequency and zero frequency, distance from center frequency to one and from center frequency to zero. This is the more precise answer. Difference between 1 and 0 is 2 times the deviation. So deviation is from center frequency to 1 or to 0. So distance between 1 and 0 is 2 times the distance. So this is the correct. What frequency bands can you use in USA for free without license? Again, in this ISM band document, you scroll up to, I don't know, America. It's somewhere here. Blah, blah, blah. Regulation in United States. And it says basically some low range, 3, 9. So I think it is this, and this. You can find them here. So, you know, if you try. 902, 2.4, and 315 is America. Basically, the ones that are not in Europe, except 2.4 gigahertz, which is international. Next, given the center frequency 868.3 megahertz, deviation 100 kilohertz, bitrate 50 kilohertz, what is the approximated width of transmitted signal and frequency domain? You know, it's simple. Deviation plus bitrate, I think, is the formula. Tx bandwidth is 2 times deviation because it's to the 0 and to the 1, and half of bitrate plus half of bitrate, 2 times deviation 200 plus 50 is 250. So this is the correct answer. Increasing the deviation. If you increase the deviation, on one hand, ones and zeros are further away, so it would be easier to distinguish between them. But the wider the deviation, the wider also the Rx bandwidth, which means more noise can get in. So, you know, you open the gate for the signal, you also open the gate for the noise. So this impact is hard to determine. This is why deviation should be equal to bitrate or 2 times bitrate, something like that. Next is, what is the maximum transmit power in 868 megahertz band for non-specific devices? Oh, and this is in dBm, so it's plus 14 dBm. You go to this document, it was actually written there. So let's check out how many answers to my test I got incorrect. You know, if I make mistakes here, it means you also could make mistakes. So, oh, no mistakes, 100%. And I made this test 2 years ago, so, you know. So it's best to just do the test as early as possible. Don't postpone it. Don't do it, you know, at the end of semester, because right now maybe you could only answer half of the questions. By the end of semester, I'm afraid that you will have forgotten 90% of this information. However, if you do the test, you will revise the material and you will actually remember it for the rest of your life. Okay, so please do the test, you know, maybe soon or now. So we had question in the test. You can do the test tomorrow or next week or after 5 weeks, but it's best to do it as early as you can. You know, just sit down, do the test. If you don't know the answer to the question, just Google it. And there will most probably be an article which explains the answer to the test even better than I have explained it to you. Okay? So I hope I answered your question. So the document that you need to use, again, is ISM bands TI, Texas Instruments. And the first document is the right one. So, here you can find, answers to something like 3 or 4 questions in the questionnaire. Okay. Any more questions? Okay, then maybe we finish this lesson and, good luck with the test and so on. Okay? Then goodbye. Yes.